In this video, we will be discussing the trigonometry of right triangles. Our first topic is going to be the trigonometric ratios. We're going to begin by introducing the three basic trigonometric ratios. These are sine, cosine, and tangent. For each of these ratios, we will be applying them to an angle. Throughout this video, we will be referring to an angle as theta. Thus, when we say sine theta, we are referring to the ratio between the sides that the angle theta in a right triangle will give us. But I will get into that in a second. To relate this back to something that we've already learned from, let's take a look at the unit circle. In this circle, we know that drawing lines from the origin to the circumference of the circle gives you an angle that we will be referring to as theta. That can be used for various purposes. In this video, we can see that by drawing a line at one of our angles to the circumference, we are given a straight line going from the origin to the circle of radius 1. To connect this back to our trigonometric functions, we are going to take one of the lines of the unit circle and we are going to draw a line down from the intersection between the theta line and the circle so that it connects perpendicularly with the x-axis. This line creates a right triangle, with the hypotenuse functioning as the radius and one of the sides being the height of the triangle and the other being the base along the x-axis. As we know, the three trigonometric ratios are sine, cosine, and tan theta, and each of these represent the ratios between the two sides on this right triangle. Sine theta is the opposite side over hypotenuse. Cos theta is the adjacent side over the hypotenuse, and tan theta is the opposite side over the adjacent side. A good trick to remembering these ratios is SOHCAHTOA, that being a short word whose letters spell out the ratios. Given this, we are going to learn the three other trigonometric ratios, those being cosecant theta, secant theta, and cotangent theta. Cosecant theta is equal to 1 over sine theta, while secant theta is equal to 1 over cos theta, and cotangent theta is equal to 1 over tan theta. A good trick to remembering which of these ratios correlates to the original three ratios is to look at the third letter in each word. Cosecant's third letter is an S, denoting sine theta. Secant's third letter is C, standing for cosine. And cotangent's third letter is T, which stands for tangent. Now, let us move on to some practice problems. In our first practice problem, imagine that Superman is told that he's 24 miles away from the base of a building that is 7 miles high. The building is on fire. Superman is able to see his grandmother calling for his help. Unfortunately, the villain is holding Superman captive and says he can only let Superman go save the building if Superman is able to tell the villain the trigonometric ratios of the angle between Superman's line of sight and the ground. Pause the video and have a go at it yourself before continuing. Now, looking at the solution, we first need to identify what the sides of the triangle are in relation to the given angle. Next, we will recall what the trigonometric ratios are for these sides. We know that sine is opposite over hypotenuse, thus sine theta is this. Cos is adjacent over hypotenuse, so it is this. Tan is opposite over adjacent, so it is this. Now look at the reciprocal functions cosecant, which is the reciprocal of sine, so it is this. Secant is the reciprocal of cos, so it is this. And cotangent is the reciprocal of tangent, so it is this. Now, looking at practice problem 2, we are given the cosecant theta ratio of 5 over 4. And we are asked, what is the sine theta of this? This problem is a good test of fundamentally approaching basic problems with these trigonometric ratios. If a student is able to quickly notice that cosecant equals 1 over sine, they will have a much easier time with problems in the future. So, the solution to this problem is simply the reciprocal of the cosecant ratio, because sine is the reciprocal of the cosecant ratio. So we therefore get that the sine ratio is 4 over 5. If we know that the sine ratio equals 4 over 5, we know that it can be very easy to fall into the misconception that the opposite side is 4 and the hypotenuse will be 5. But sine is only a ratio function, so the opposite side could possibly be 8 and the hypotenuse could possibly be 10. But we can still draw out the triangle in terms of its shape, but not necessarily its scale. Now, moving on to a quick calculator tip, something that is worth noting is that if you are ever using your calculators a lot, people are often tricked into using sine to the negative 1x or cos to the negative 1 x, believing that these functions represent cosecant and secant. Rather, these functions are the inverse of sine and cosine, and what exactly that means is not related to this topic, but it is good to remember that if you're calculating cosecant of 45 degrees, you would want to plug in 1 over sine of 45 degrees. Now, moving on to our topic number 2, special triangles. Certain right triangles have ratios that can be calculated easily from the Pythagorean theorem. A squared plus b squared equals c squared. Since these triangles are used heavily throughout all of pre-calculus, it is good to understand how the major ones work. Today we will be discussing the isosceles right triangle and the 30, 60, 90 right triangle. The first triangle we will be discussing is the 30, 60, 90 degree triangle. And the reason it's called this is because its angles are 30 degrees, 60 degrees, and 90 degrees. What we want to prove is that the side lengths opposite of the angles 30 degrees, 60 degrees, and 90 degrees have very specific ratios to each other. So suppose that the hypotenuse has length x, which is opposite to the 90 degree angle. If that has a length x, then the shortest side, which is opposite of the 30 degree angle, has length x over 2. And the side that is opposite of the 60 degree angle is of length x root 3 over 2. That's what we're going to prove in this video. Now, let's start with an equilateral triangle, ABC, of side length 1. And just as a reminder, we know a triangle is equilateral if all its sides and all its angles are equal. What we want to do is draw a perpendicular bisector DB from its peak to its base. Now, given this new triangle, from the trigonometric ratios that we already know and the Pythagorean theorem, we can find out that the length of DB is root 3 over 2. Since DB bisects the angle ABC, we obtain a triangle with angles 30 degrees, 60 degrees, and 90 degrees. For the lengths, we can also look at the sides with ratios to each other of x, 2x, and x root 3. What is cool about these ratios, once we have determined them for any specific type of triangle, and remember this applies to all right triangles, not just the special ones once you determine their ratios, is that given a certain proportion of its sides, it may be 3, 4, 5 triangle of a 30, 60, 90 triangle, we can take any constant number like 10 or 2 or 3 or 7 and multiply that factor and plug it into the x value that we have, and the triangle will still be a right triangle of this that maintains these consistent ratios between its sides. Now, looking at our second special triangle, we're going to be discussing the 45, 45, 90 triangle, which is named this similarly because of its degrees 45, 45, and 90. What we want to find is the ratio between the sides and the hypotenuse. To achieve these ratios, we want to begin by drawing a square of side length A, or 1. The side length is irrelevant, but let's set it to 1 now for simplicity. Now, given this square, we want to draw a diagonal line connecting the opposing vertices in the square. From what we know about the square, that being that the sides are always equal, we now know that the two bases of a right triangle are equal. And if we set our third side to be the variable x now, in order to solve for the third side or the hypotenuse, we have to use the Pythagorean theorem. We get the equation a squared plus a squared equals x squared. And in solving this equation, we learn that the diagonal has a length a times root 2. Or, in the case of setting these individual base and height components to 1, we get that it equals root 2. And as we discussed before, once we find the ratios of this type of triangle, it can be applied to any similar triangle, meaning a triangle of equal angles. Now, looking at some of the applications of trigonometry of right triangles, one of the most heavily used applications of right triangle ratios that we have encountered throughout this video is angle of depression or angle of elevation. This is a major application, and it goes across many different subject fields other than just math. Imagine that you're standing on a horizontal plane, like the x-axis, and there is an object in front of you, but it is also above you, as shown in this picture. That means that there is an angle of elevation between the two of you. Similarly, if you are on a plane and there is an object in front of you, but the object is also below you, there is an angle of depression between the two of you, as shown in this picture. To demonstrate this, we will go into a few practice problems. The first practice problem we will be looking at is this. Imagine that some construction workers are given a ladder of length 12 meters and prop the ladder at an angle of elevation of 30 degrees above the x-axis against a building. To what height will it reach on the building? How far away is the base of the ladder from the base of the building? I encourage you to pause the video here and try it on your own before continuing. Looking at the solution to this problem, given that this is a 30 degree, 60 degree, and 90 degree triangle formed by the ground, the building, and the ladder, and the hypotenuse is equal to 12, we can find the values of the other triangle sides. And what we want to do is solve this through ratios between the sides of the triangles. And if we are ever unsure, we can rederive these values from the equilateral triangle. So we know that the triangle sides are x, 2x, and x root 3, pardon. Thus, if we see that 2x equals 12, then what is x? X is going to be 6, and x root 3 is going to be 6 times root 3. In this chapter, we will be discussing the inverse trigonometric functions and right triangles, the inverse functions being inverse sine, inverse cosine, and inverse tangent. The objective of these functions is to obtain the original ratio, or is to plug in the ratios and be able to pump out a number. And by to fully understand this, we need to first complete a proof to understand these ratios. Let's begin by addressing the sine function in particular. Restricting the domain of this function to angles between negative pi over 2 and pi over 2, we get the values between negative 1 and 1 all only once. This is shown either on the Cartesian plane by graphing out y equals sine x, in which we see the graph going from negative 1 up to 1. But it can also be depicted on the unit circle, in which it draws a half circle on the right side of the unit circle. When using these inverse trigonometric functions, we always want to set specific domains in order to create to allow these functions to meet the basic requirements of what a function is, meaning that it can only have one output for any specific input. So next we will do the same thing with cos theta equals y. And here, looking on the Cartesian graph again, we can see that the graph goes between a maximum of 1 and negative 1. And again, we set a domain so that for when we create an inverse function, there's only one possible output for every input that we put in. Now, looking at tan x equal to y, this is a bit different of a function because the range is all real values rather than negative 1 and 1. Thus, we are going to restrict the domain from negative pi over 2 and pi over 2 in order to capture all the values in the most concise domain. The only difference is that there are no distinct bounds on our range. So, now that we've established the bounds on which these functions can be used, we can see that we can show our classical functions in their inverse form by denoting a negative 1 next to the function, and we can switch the y and x value. The x would be the angle and the y would be the output ratio of the original functions. To see how inverse trigonometric functions can be applied, we will look at a practice problem. So suppose there is a woman standing at the ground level, looking up and marveling at a beautiful bird flying through the air at a distance on the x-axis. The bird is 9 meters away from her, and in the distance on the y-axis, the bird is 5 meters above her. Her line of sight goes directly to the bird, creating a right triangle. What is the angle of elevation of her line of sight? Now, I encourage everybody to pause this video as per normal and see if you can do it on your own before continuing. Now, moving on to the solution of the problem. Because what we are given is the two base lengths of the triangle, it is most useful to use an inverse tangent function, but we could potentially use any of the functions because we can always find the third side using the Pythagorean theorem, given that this is a right triangle. So suppose that we are using sine negative 1 of y equals x. Y is the hypotenuse, or is the opposite over the hypotenuse, pardon. And so we can therefore understand that the ratio is going to be 3 over 5. And using our calculator, we can press second, sine, and plug in this ratio for ourselves. And what we end up finding is that the answer is that the angle of elevation is 36.87 degrees.